Greetings, chemists. This is going to be a deeper dive into the topic of ionic bonding. So in the last video, we talked about the idea that ionic bonding interactions happen because of a strong nonmetal, strongly electronegative nonmetal versus a weakly electronegative metal. And we showed, and here's the periodic table, so we showed that it had to be someone from this side, the yellow side, on this periodic table anyway, but past that little green line, these semi-metals are from boron, silicon, arsenic, etc. If we go to the right of that, you're strong enough to steal. If you go to the left of that, you're weak enough to be stolen from, and that's what creates an ionic bond in the first place. Okay, so we're going to get a little more depth to that. Here is the idea. We said that the noble gases are stable, and again, the octet is king here. So a neon atom is stable because of 1s2, 2s2, 2p6, that it fills all of its outer energy level. The energy level 2 has 2s electrons and 6p electrons. That's 8. All right. If you do argon, argon is stable. It's 1s2, 2s2, 2p6, 3s2, 3p6. So all 8 electrons on the third energy level, similar to all 8 electrons in the second energy level in the neon, that's how it becomes stable. If we go to krypton, and I'll do the outer energy level. Now, remember how we fill 1s2, 2s2, 2p6, 3s2, 3p6. It's 4s2, 3d10, and 4p6. And you might think, oh, well, that's 18 electrons on the outer level, except that that's the third energy level, right? I know we fill it after the fourth energy level, but in terms of bonding, what we tend to consider are those 2 4 energy level electrons, and those 6 4 energy level electrons. And because of the way that orbitals are filled, it will always be the p electrons and it will always be the s electrons that matter, because all other energy levels within that atom will be, like the 3D is lower than the 4 in terms of energy. So that's the concept of an octet. If you get all 8 of those s electrons and those p electrons, the ones on the outer energy level, you will be stable. The only exception to this is helium, because helium doesn't have a p orbital to draw from, because the first energy level only has an s. So helium has a 1s2 configuration, and that's all it needs to be stable. But for everybody else, the upper last energy level is composed of a s electron, an s orbital, and a p orbital. Okay. With an ionic species, they're trying to reach that. So let's look at the example we used in the last video, which was fluorine and cesium. Because the electrons that I care about are those 8, I'm only going to consider those 8. And chemists have come up with a way of a shorthand of drawing this. If you had, remember what the boxes used to look like. This was an s orbital, and then there was a p, had 3 boxes, right? That was our orbital diagram. And you could fit 2 electrons in an s orbital and 3 pairs in a p orbital, okay? Or a p sublevel. So those 4 boxes, I'm going to pretend my fluorine has 4 sides. And I'm going to put 2 dots on each side. Or I can put up to 2 dots on each side. That would represent all 8 of those electrons. Now, when we look at fluorine, remember fluorine is not neon. Neon is 2s2, 2p6. Fluorine is 2s2, 2p5, right? That's why he's so reactive, is he's missing an electron. So he actually doesn't have all of his outer electrons. He only has 7 of them. Okay, that's important. When we look at cesium, cesium is a 6s1. He only has 1 electron on his outer shell. I'm just going to draw that as a dot. Okay? Well, when fluorine and cesium interact, fluorine steals cesium's electron. We talked about it in the last video, and why it does that. But the fluorine gains it, the cesium loses it. Now that was a negative charge that fluorine took. Fluorine used to be neutral. Fluorine had 9 protons, 9 electrons. Remember, because there's 2 in the inner level. And so fluorine was not charged, but when he takes an extra negative, he has now 9 protons and 10 electrons, and now he becomes -1. So here's how we're going to do that. We're going to draw the fluorine, like so, and we're going to put a little -1 right there to indicate that he has stolen an electron. Cesium. Cesium had an electron. He had a negative charge. Now, he actually had like 55 of them, but that was the one in the outer shell. He also had 55 protons. So cesium used to be neutral. But fluorine took away one of his negatives. Now there's only 54 electrons and 55 protons. So he is left over +1. Okay. Well, those guys will now stick together because they have this attractive force between them, right? Positives attract negatives. And there's 1 each of them. So we will write a formula for cesium fluoride. And the formula goes like this. We put the positive ion first. We put the negative ion second. And typically when we talk about ionic bonds, we talk about, we don't change the name of the positive ion. We say it's cesium. But we do change the name of the negative ion. This was fluorine, but we're going to change his name to fluoride. Cesium fluoride. So if you've ever brushed your teeth with fluoride toothpaste, that's because those were these negative fluoride atoms and not neutral fluorine atoms, which is very good because if you tried to put neutral fluorine into your mouth, it would destroy your teeth and your tongue, and you would probably, you probably wouldn't survive it. Okay. So thank goodness you're getting fluoride ions, which have their own problems but are not nearly as dangerous because they filled their octet. They have their electrons. They're not going to try to steal electrons from the atoms in your teeth, your tongue, or something. Okay? Now, what if we did this? What if we took some magnesium atoms and some chlorine atoms? Magnesium, let's look at his outer electron configuration. We can do it with the periodic table, actually. Magnesium is the second row. So that's 3, 3s1, or 3s2. He has actually 2 electrons on his outer energy level. So I'll draw those like this. There's magnesium's electrons, 2 dots. Chlorine, we can do chlorine the same way. Count from left to right. 1, 2, 3, 4, 5, 6, 7. Chlorine has 7 outer electrons, right? He has all of the inner ones, but those are not the bonding electrons. So let's draw that. Remember, you can only fit 2 per side. Okay, when they interact, well, chlorine's a non-metal, very strong one. Magnesium's a metal, very weak one. So clearly chlorine will steal from magnesium. If he does, it looks like this. Chlorine takes that electron, so I now have 8. Magnesium loses. Now chlorine, in that case, is full. It's got his octet. Stable. Magnesium is not, still unstable. So that's not helpful. But you would never have, let's suppose you had a tank of fluorine, or chlorine. There's chlorine in it like a tank. And over here you have a block of magnesium. Magnesium's a solid, chlorine is a gas, and you spray some chlorine onto this magnesium. Well, you would not just get 1 atom of chlorine, 1 atom of magnesium, you would have a whole bunch of them. So what would happen is you would have another chlorine atom come in. Well, this one hasn't absorbed an electron yet, so he still only has 7. Magnesium still has 1, and this is still stronger than magnesium, so he will steal that last electron, take it away, like this. So in order to satisfy everybody, what would happen is the chlorine atoms would steal all of the magnesium's electrons, each of them would steal 1, and it would take 2 chlorines to fully steal all of magnesium's electrons. Okay. What would happen with the charges? Magnesium just lost 2 negative charges. Well, that means he would now be positive 2. Chlorine, this one only took 1 electron, so he only becomes -1. Chlorine, this one only took 1 electron, so he only becomes -1. But now they're like magnets, right? Now this guy is positively charged, this guy's negatively charged. They're going to stick together. But they won't stick together 1-to-1 like cesium fluoride. They will stick together with 2 chlorines and 1 magnesium. Here's how we write that. 1 magnesium, 2 chlorines. We put a little subscript underneath the chlorine. And that would be the formula for magnesium chloride. And notice when I say it, I'm writing it like this. Magnesium goes first, the positive ion goes first. We don't change its name. Cesium was still cesium, so magnesium is still magnesium. We don't change his name. Chlorine, though, used to be chlorine, but once he gains that electron, he becomes chloride. That's it. So if you saw a formula, let's do aluminum chloride, you could actually predict the ratio of the atoms. Let's look at it. Aluminum, Al, has 3 outer electrons. Chlorine has 7. He steals, he gives up. Well, this chlorine can steal 1 electron. There's 2 more. It would take 2 more chlorines to finish that. So we should have, for aluminum chloride, AlCl3. There should be 3 chlorides for every aluminum. If you're ever worried about what charges things should be, notice that the cesium, which only had 1 electron to start with, became a +1 ion. The magnesium that had 2 electrons to start with became a +2 ion. The aluminum that had 3 became a +3 ion. We didn't show that, but if 3 electrons go away from it, you would be left with an aluminum +3. The chlorine, which had 7 electrons, would form a -1 ion because he's a nonmetal. He would steal. He would gain an electron. We can look at oxygen. Here's an oxygen atom. Oxygen has 6 electrons. It's a nonmetal. It steals. So if you ever had an oxide ion, it would mean it gains 1, 2. Well, that would be a -2 ion. And so if we look at the periodic table, we can see this. Watch. Everybody in this first column was an S1. They only had 1 electron. They will all lose 1 electron. So the first column tends to be a +1 ion column. When we go to this column, these is column 2, they tend to be +2 ions. When we go to this column where fluorine is, where they all have 7 electrons, they only want to gain 1 electron. This tends to be a -1 ion column, at least in the nonmetals. The oxygen is -2, the sulfur is -2 generally when they form ions, although sulfide is a sort of a rare ion. Nitride would be a -3 ion. Now these green guys don't form ions very easily, certainly noble gases don't, and there's different rules for the transition elements, which we'll do in another video. Okay, that's the basics for ionic bonding.